Okay, in the last video we looked at generalized combinations. That was the idea of choosing combinations where there were certain elements that were allowed to be repeated. In this case, we're going to be looking at generalized permutations. Remember that the difference between permutations that we have here and combinations is that with a permutation the order matters. When we were picking coins, of different types, it didn't really matter whether we picked the pennies first and the nickels second, or the pennies second and the nickels first. But when we're making strings like OMG or LOL here, the order of the string certainly does matter. And mostly what we're going to focus on this semester here is looking, and in this video, is looking at just reordering strings with repeated letters. Okay, now up until now, we've had no problem figuring out how many ways we can distinguish or rearrange, three characters, right? We know that we have three choices for the first, two choices for the second, and one for the first. We know that 3 factorial is the way to rearrange 3 different objects, right? So this is really nothing new. But in a case like this, if I were to sort of think about these L's as different, like if I had actual pieces of paper and one of them was colored green and one of them was colored blue, right? Then if I did 3 factorial, right? If I had 3 choices for the first one, I could choose the L first, the green L, then I could choose the blue L second, and then I could choose the O, right? But I also, as an equally likely scenario, could choose the blue L first, and then the green L second, and then the O third. Okay. Now, if I just did 3 factorial for these, and if I had different, somehow distinguishable L's, whether they're different colors or sizes or anything, these two would be counted as different, even though they really represent the same string, right? Because we know these L's are exactly the same. I can't tell if these two L's got reversed. Okay. So if we think about the pattern for rearranging the letters LOL, we know that we could have LOL, we know that we could have LLO, we know that we could have OLL. There's really only 3 spots for that O to go, and then the other 2 are L's. Okay? Now, each one of these is going to get counted twice, because if I were to swap the L's, right, and they were distinguishable, they would look different. So if I just did 3 factorial, I would be counting each of these twice, right? And that's because there's 2 factorial ways to rearrange the L's. The 2 L's. So the idea is we take the 3 factorial, treating them all as distinguishable characters, but they're all going to be overcounted. And in this case, they're going to be overcounted by 2 factorial ways because of the 2 L's. Okay? The general pattern for this is if you had n different characters or objects, and you had n sub 1, n sub 2, n sub 3 of each type, right? And this would go on ... to n sub k, right? Then the formula becomes n factorial over n1 factorial, n2 factorial, all the way up to n sub k factorial. Okay? The idea is that any group of letters that are repeated, if you swap those 2 letters, since they're not different colors, they're all the same and they look the same, we could rearrange that individual group n sub I factorial times. Okay, so the idea is here basically similar to how we got the combination formula from the permutation formula, that we overcounted and then we divided by the number of different, seemingly different strings that really are the same. Okay, this is the general formula we're going to follow. Now, the 1 O, right, could go down as 1 factorial, right? But that's sort of unnecessary. If a character only shows up once, there's not much point in putting 1 factorial in there. Okay, so let's look at some examples, and hopefully you'll have a better sense of how this formula here is actually going to work. For something like logic, there's 5 characters and they're all distinct. So there's 5 factorial ways to rearrange the letters in logic. Now when you look at the word discrete, like in discrete math, there are 2 E's, right? There are 1, 2, 3, 4, 5, 6, 7, 8 characters. So if we treated them all as unique characters, there would be 8 factorial ways. But every time I swap these 2 E's, I won't be able to tell the difference. So if I count swapping the 2 E's as a different string, it's not going to seem different. So I have to undo that overcounting by dividing by the 2 factorial because there were 2 e's repeated. Okay. Now let's look at a third example down here where we have more repetition. Okay, I have 1, 2, 3 e's here, and then I have 1, 2 r's here. Okay. Now the word creeper is actually 7 characters, so I start off with 7 factorial. Right. Every time I rearrange one of the 3 e's, it won't look different. So I have to think about the 3 factorial ways those e's could be arranged, and then any way I rearrange the 2 r's, I won't be able to tell the difference. So you can sort of give yourself a little bit of partial credit and explanation here by explaining where that 3 and 2 came from. Okay, the c and the p can only be, they're only repeated once, so there's no point in putting a 1 factorial in for those. Okay, now when you get to a word like Mississippi, which has a lot of repetition, right, you're going to have just more writing to do. Now the word itself has 4, 8, 11 characters, so we're going to start with 11 factorial on the top. Now there's 4 i's, there's 4 s's, and there's 2 p's. So we're going to have a 4 factorial for the i's, we're going to have a 4 factorial for the s's, and then we're going to have a 2 factorial for the p's. Okay. Now there's other applications for these. This is sort of the intro level, and it kind of gets the point across with something that nice that you can sort of see and relate to, and that's all that we're really looking for in this video. Okay, so make sure you practice these as always, and look at some variations and some other examples. Okay, good luck.